All right, let's take a look at coding challenge number 6. Now, here we're going to use a technique called numerical methods, which basically means we're going to get the computer to do the equivalent of flipping a coin a bajillion times, and using that large set of randomness to get a decent estimate of something important, some real world thing. So we've got two parts to this. The main thing, the actual assignment, is the birthday problem, which I'll walk through in just a sec, but let me use the going beyond part of this because it sort of more directly addresses this issue of how we use numerical methods. So the second part of this assignment, if you choose to go beyond, is to estimate pi using randomness. So basically what I want you to do is to, let's imagine, so this square we've got, we can put a whole bunch of random points in this square, and then we can ask how many of those are within a circle. So we've got a bunch of points, some are in the circle, some are outside the circle, and that ratio we can use to estimate pi. Now probably we're going to end up using that to estimate 1/4 of the value of pi. So just a little hint, you're likely to run into something where you're going to get an estimate of like 0.7, and then you have to multiply that by 4, and it's going to come close to 3.14. And another thing, as long as I'm thinking about it, is in R, there is a built-in for pi. So if you just type pi, that'll give you pi. But to estimate pi, we're going to, like I said, make a whole bunch of random points, figure out how many are inside that circle, and then do a little bit of light math to spit out an estimate of pi. So I created a function earlier to do that, and you can see that when I have that run 1,000 times, pulling 1,000 points, I get a range of estimates for how big pi might be. And some of those estimates are not great. 2.972 is pretty far off from pi. 3.3 is pretty far off from pi. But you can see that we have a lot that are pretty close. So we got 20 estimates that were about 3.152. We got 46 that were 3.144, 33 of 3.14. So we've got a lot of estimates that are quite close. We ran 1,000 different estimates, and some were far off, but on average, pretty good. If we ran just this estimate pi function on a million points, we would get a more accurate estimate. In any case, that's the gist of numerical methods. Bunch of randomness and then a little interpretation to pull out something useful. In this case, an estimate of pi. Now, how useful is it to estimate pi? Not super important, but we're learning the tools. We're not actually estimating pi. Now, another sort of fun problem is the birthday problem. And what this is kind of a surprising statistical realization that in any group of people, it is surprisingly likely that two people in that group will share a birthday. So if I were to ask, say in our class, how many people share my birthday of November 24th, odds are pretty low that we're going to find someone else with that birthday. Right? Each of us has 365, 366 possible birthdays if you were born in a leap year. 366 possible birthdays, so 10 people in the room, it's not very likely that one of them has the same birthday as me. But any two people sharing the same birthday as each other, that is much more likely. So if we look at this nice little plot that someone made on Wikipedia, this is the calculated probabilities of these things, and basically when you have a room of 23 random people with different birthdays, there's about a 50% chance that you will find two people in that room who share the same birthday. Right? Notice, not the same birthday as one specific person, but we can find one person and one other person who share the same birthday. So you might check, how many people match my birthday? None. How many people match someone else's birthday? None. But we repeat this, and we repeat it a few times, and the probability goes up, right? Finding two people who have the same birthday is a much easier problem than two people who share my birthday. That's kind of the intuition that makes this surprising result work. But what we're going to do is we are going to use R to avoid having to calculate these probabilities by hand using all these, permutations and combinations and stuff that I learned a million years ago, but I don't remember. So we're just going to get R to chunk through a bunch of stuff and get close. So I've given you a little bit of structure here to set you up. So let me walk you through a little bit of pseudocode, partial code on my computer. So we clear everything out. I'm not going to do that now because I do want to show you a little bit of other stuff. But we're going to make 3 main functions that are going to do most of our heavy lifting. Birthday sample is going to take some group and it's going to come up with a bunch of random birthdays. So I'm saying by default, if we just say give me birthday sample with no arguments, it's going to assume 23, right? So if we run this a bunch of times with a group size of 23, about half the time we should find 2 people who share a birthday. And so birthday sample, we're coming up with a random list of birthdays. Birthday match, we're going to look through a random list of birthdays and see if any 2 of them are the same. And then many samples is how we're going to actually use this randomness to come up with a good estimate. Right? So if we run a sample once, we may or may not find 2 birthdays that are shared. But if we run this a million times and we ask how many of those repetitions result in something, what we should find is that with a group size of 23, about half of them have, a true result coming out of birthday match. So birthday match, we're going to check a bunch of stuff. And so for many samples, basically what we can do, a lot of the stuff I'm skipping over here, but the repetition part of this, we can create these samples, and let's say we use sapply. That's probably the most reasonable way to do this. So sapply is going to, by default, take some numbers and plug them into a function as the arguments. So the numbers we're going to deal with here is we're going to use the rep function. We're going to repeat our group size. So let me get out of your way. We're going to repeat our group size, let's say, 10 million times. I'm going to say 10, so we're not flooding the screen. So rep 23, 10, we just get 23 10 times. So this is going to, by default, with our default arguments, plug a birthday match for some sample input. I have to do this. I do have to change things a little bit here. We'll explain that in a sec. But basically, we're going to repeat some stuff a bunch of times to get something. So actually what I need to do here is not birthday match, but birthday sample. Right? So this is going to give us a whole bunch of samples, and then we're going to go through each of those samples, and we're going to ask, is there a match from these? So how do we do that? I'll leave that to you. We'll talk about it in class if you run into problems. So, long story short, we're going to make a bunch of random birthdays. We're going to check those random birthdays to see if there's a match, and we're going to repeat that procedure a bunch of times, and then we're going to use that to spit out some estimate. So we should return something along the lines of, let's call it some estimated probability. We should return something close to 0.5 if we're putting in a group size of 23. If we're repeating that once, right, we're either going to get 0 or 1. If we repeat it a bajillion times, we're going to get something very close to 0.5 with a whole bunch of decimal places, but it's going to take a long time to run. So what you should do ultimately is run something like many samples 1,000 times for a group size of 23, and you should get something like 0.50015, or something like that. Right? Probably actually a little further away than that, but that's the gist of it. Right? So you're going to repeat this process. You're going to get the computer to repeat this process a bunch of times to give you an estimate of this probability without having to do the math to get that estimate. All right, so if you have any questions, let me know in the usual places, and I will talk to you in the future.